Hello everyone, welcome back. This is Dr. Gallenstein. Thank you for joining me again. In today's lecture, we are going to begin to discuss utility maximization. Utility maximization. All right. Oh, not very good at spelling, am I? Maximization. All right, so we're going to look at utility maximization today. We're kind of bringing together a lot of the things that we've gone over so far in the course. So you remember at the beginning of the course we talked about kind of how economists think, right? That we like to think about human decision making in terms of rational choice theory, right? So we consider rational agents with well-defined preferences, making decisions in the context of scarcity, so subject to constraints. That a rational agent always makes decisions that give them the most of what they prefer, given the constraints that they face. We talked about how they make decisions on the margin. That is, that they use marginal analysis. We make decisions on the margin, and we make optimal decisions. Okay, and then we did some mathematics review where we learned about functions, and we learned about how to optimize a function and how to optimize the function in the context of a constraint. And then in our last lecture, we started to talk about what do preferences look like mathematically, and then finally we discussed what a utility function is and some of the characteristics of the utility function. Well, now we want to put all of this together and to create a mathematical model, a mathematical way of expressing rational choice theory, a mathematical way of modeling human decision making, where we bring together everything that we've gone over so far in the course. Okay, what we're going to start with, we're going to look at a utility function. A utility function that takes goods as inputs. And it gives us utility as an output. This utility function, it captures the preferences of rational agents. It captures the preferences of rational agents. Okay, we talked about what some of the characteristics. The utility function has to have a positive first derivative. Because, like we said, we assume non-satiation, that is, more is better. If more is always better, then your utility always has to go up as you get more of a good. And if we wanted to graph this, we would get a graph that looks a little bit like this. It's always going up. As I get more of good one, my utility always goes up. Okay, so that's a positive first derivative. We also said that it needed to have a negative second derivative. This is to capture the diminishing marginal utility. Diminishing marginal utility. This gives us a concave function, which you'll see here. Okay, so what we did in last lecture is we took some of those principles about rational choice theory and the way that people value goods. We took that and we captured it all into the form of this utility function. Well, now what we want to start to do today is we want to take it to the next level. Now we want to look at how people make decisions. And if you remember, we said that people make decisions by getting as much of what they prefer as they can, given their constraints. So another way that we're going to put this, and in fact we're going to put it this way for the rest of the course, is we're going to talk about agents maximizing their utility. That is, we're going to try to find what number of, or how much of good one or good two and good two will the person consume in order to maximize their utility. Because we want to study decision making. We want to know, how do people decide how much of good one to consume and how much of good two to consume? Well, if they are rational agents, they will choose good one and good two such that it maximizes the utility. They will choose the number, how much of good one and good two an agent will consume will be based on the amount of good 1 and good 2 that will maximize their utility. That means give them the most amount of utility that they can possibly achieve in the context of constraints or subject to some constraint. All right, so that's what we want to do. We want to set that up. We want to look at how do we maximize, how do we find the value of the goods, these inputs, that will give us the maximum amount of utility. All right, so that's what we're going to do. We're going to look at that. But now, like I said, agents make decisions in the context of constraints. That means they face constraints. And so we need to add some constraints onto the decision-making process. So if we're looking at just this generic example, we want to know how much of good 1 and good 2 will the agents consume in order to maximize the utility. But when agents make decisions about how much to consume, they always make decisions given a constraint. And their constraint is going to be their budget constraint. That is, they're constrained. They can't buy an infinite amount of good 1 and good 2 because they're constrained by their budget. They're constrained by their income. Okay? And so what we're going to do today is we're going to look at how do we choose good 1 and good 2 that maximize utility subject to a budget constraint. Now, so far in the class, we've already talked a little bit about utility functions. And so we're going to start today's lecture by talking about the budget constraint. So let's do that now. Let's start by discussing a budget constraint. Okay, so like I said, if we wanted to model the decision making of an agent, that is, we wanted to understand let's say how much of a good they're going to consume, then we need to know the context in which they're making that decision. We need to know the constraints that are on that decision. All right, so let's do a very, very simple model. Let's say that eventually we want to maximize someone's utility. And let's just use the example we used before. Let's do coffee and bagels. That means we want to know how many cups of coffee and how many bagels that an agent will consume in order to maximize their utility. Well, whenever we make decisions about how much coffee and bagels to consume, we always make it in the context of a constraint. That is, we make it in the context of having some budget. We can't spend an infinite amount of money on coffee and bagels. Well, how would we model that? How do we mathematically represent that constraint? Well, the best way to represent that constraint, or just a simple, straightforward way of representing it, is that first we think about how much income we have. So let's define some things. I is going to be income. We could say this is total income or disposable income, or whatever income we have available to spend on coffee and bagels. Okay, so we have our income. All right. And then we know what C is. C is coffee, right? And B is bagels. Let me just define two more things. PC is going to be the price of coffee. And then PB is going to be the price of bagels. Okay, so with these terms defined, then we would know what is their constraint? Well, they cannot spend more money than they have on coffee and bagels. So how much money would I spend on coffee and bagels? Well, it would be the price of coffee times the number of cups that I buy, plus the price of bagels times the number of bagels that I buy. And so if I say that we face a budget constraint, that means that I cannot spend more than I have. So that means my income has to be greater than or equal to what I spend. I cannot spend more than I have. So then this expression here will be our budget constraint. So thinking ahead, right? If we wanted to maximize, that means we wanted to find the number of cups of coffee and the number of bagels that gives the agent the maximum amount of utility. We have to do that subject to a constraint. That is subject to the budget constraint. That is subject to the fact that income must be greater than or equal to the amount of money that I spend on coffee and bagels. All right. So what we're going to do is we are going to perform this. We're going to find C star and B star, that is the number of cups of coffee and the number of bagels that I would consume to maximize my utility, subject to the constraint, subject to the budget constraint. Well, that's what we're going to do. We're going to work our way up. We're setting ourselves up to do that. This here will be a mathematical model. This will be a mathematical model of human decision making. All right, this will be a powerful tool that we will use again and again in the course. Okay, with all of that said, before we do this maximization, let's do some background. Before we do this maximization, let's do some background work. I want us to have a good understanding of what this budget constraint is. I want to look at some graphs so that we get some intuition on the budget constraint and on the way that utility and the budget constraint interact with each other. Okay, so let's do that. Let's get some of this intuition first before we move on to the actual maximization process. All right, so let's do that. So we have our budget constraint. Income has to be greater than or equal to the amount of money that we spend on these goods. All right, so that'll be our budget constraint. Well, as we discuss this, let's bring back the graph that we had from the last lecture where we related the possible consumption bundles. If you remember, so I'm going to draw this graph here. Okay, we have bagels versus cups of coffee. And if you remember, we drew this graph and we drew some indifference curves. And these indifference curves, they gave us all of the possible bundles, the combinations of bagels and coffee that would give us the same amount of utility. All right, so this was an indifference curve. All right, well, I want to use the same plot here to graph the budget constraint, and then in a minute we're going to combine them. Okay, so what would the budget constraint look like if I wanted to plot it on this curve, on this graph? Well, this is going to give us some nice intuition into what this budget constraint looks like by trying to answer that question. So first, let's assume for the moment that the agent will spend all of their money. And we'll come back to this in a minute, but let's just set this to an equality. Let's say that they spend all of their money. All right. Well, then I want to put the budget constraint onto this graph. If I wanted to do that, then I need to solve it for B. I need to solve this expression. Whoops. I need to solve this expression for B. So let me do that. So this would be, this would be I minus PCC divided by PB. What this gives us is a function, B as a function of C, PB minus PC divided by PB times C. All right, so now I have a function, B, bagels, as a function of coffee, and this line here is going to be the budget constraint on this curve. So let's just let's take a look at this. So the intercept is here. It's I over PB. So if C equals 0, so if C equals 0, let's say C equals 0, then the budget constraint will be here at I income divided by PB. So this would be if I bought no cups of coffee, if I spent all of my income on bagels, then this is the number of bagels that I'm able to consume. If I spent all of my money on bagels, this is the amount of bagels that I'd be able to consume. that is, I bought no coffee, spent all of my money on bagels, then I would buy I divided by PB number of bagels. That is, I'd buy the number of bagels of my income divided by the price of bagels. Okay. All right, so then if I wanted to plot this, what it's going to look like is going to be something like this. It's going to look something like this. All right, what we find down here, income divided by PC. That is, if I bought no bagels, I bought all coffee, then I would spend all of my income on coffee. I would be able to buy the number of cups of coffee that would be equal to my income divided by the price of coffee. All right. So then this line here is going to give us the outer boundary of our budget constraint. Okay. No one can afford to buy any bundle of bagels and coffee that is beyond this line. So we can't afford any combination of bagels and coffee that is beyond this line. This line here will give us the maximum, or I should say, this line here gives us all the bundles of bagels and coffee in which the agent spends all of their money. They can't afford any combination of bagels and coffee that lies beyond this line. This is the maximum. This line gives us the maximum amount of bagels and coffee that they can afford given their income I. This line here, this line in blue, we call this the budget line. We call this the budget line. We'll use L. So we call this the budget line. They cannot afford any combination of bagel and coffee that is bigger than the bundles that are described by this line, the budget line. Okay, so this line here, this is the budget line. Okay. Now, any combination of bagels and coffee that lie below the budget line, any combination of cups of coffee that lie below the budget line, they can't afford. So at the budget line, they spend all of their money. So at the budget line, they spend all of their money. At the budget line, I equals PC plus PB. B. Above the budget line, income is less than what they spend, which means they can't buy it. They cannot buy a combination of cups of coffee and bagels that would lie above I. So this is not possible. They can't buy anything out here that exceeds the budget constraint. Below the line are all the combinations of coffee and bagels that they can afford, but in which they would not spend all of their money. Okay, so that's the budget line. This area in yellow, we also call this the opportunity set. Opportunity set. Well, actually, it's the area in yellow plus the budget line. So the opportunity set is everything that they can afford, which would be everything in the yellow plus all of the possible bundles that are on the blue line, that is on the budget line. That is all the possible combinations of coffee and bagels such that they either spend less than or exactly equal to the amount of income that they have. That would be the opportunity set. Okay, now let's go a little bit deeper. Let's acknowledge a couple things here. So this equation that we have, this is the budget line. This is the budget line. Let's just note here that negative PC over PB is the slope of the budget line. Let's just put an L. It's the slope of the budget line. Okay. This slope, the slope of the budget line, we call this the marginal rate of transformation. Or the MRT. So this slope is the marginal rate of transformation. That is the ratio of the price of cups of coffee to the price of bagels. This gives us kind of the trade-off between coffee and bagels that the agent is able to afford given their budget constraint. How many bagels need to be given up in order to be able to afford additional cups of coffee? All right, that's the marginal rate of transformation. Okay, so that gives us a little bit of background about the budget constraint. All right, so now with that background, let's combine them and let's graphically discuss what utility maximization will look like. I'm going to delete this. Okay, so now let's get an idea of what utility maximization looks like graphically. All right. Okay. So here we go, coffee and bagels. Now, if you remember, we can draw some indifference curves. Before we do that, let's draw our budget constraint. Okay, or let's draw our budget line. This will be our budget line. We'll label it L for budget line. Okay, so L is the budget line. If you remember the function of this budget line, B equals I over PB minus PC divided by PB times C. All right, so there's our budget line. Everything that lies below it, the budget line and everything that lies below it is the opportunity set. That is all the possible combinations of bagels and coffee that the agent is able to afford. So they can afford everything in blue. Everything on the line and everything below it they can afford. They cannot afford anything that lies above it. Okay, now let's go back and let's remember our indifference curves. Now, so basically the budget line, everything I have here in blue, the budget line captures the constraint. So maybe I'll even write that. Everything in blue, the constraint. So this captures the constraint on the decision making. Now I'm going to use green to represent the utility side. Remember, the utility maximization process, we want to maximize utility subject to the constraint. All right, so now graphically we've represented the constraint, all right, by showing the budget line. So now what we're going to do is we're going to look at utility. So if you remember, we can have indifference curves. Indifference curves are a graphical representation of the agent's preferences. They show all the possible combinations of, in this case, bagels and coffee that give the agent the same amount of utility. So let me just draw one. So let's say this is an indifference curve. This indifference curve, we'll use the letter I, this indifference curve represents all the possible combinations, we'll call it I1, all the possible combinations of bagels and coffee that would give the agent some identical units of income, or of some identical level of utility. So if you remember, we can represent it like this. So this indifference curve is all the possible combinations of coffee and bagels that allow the agent to achieve the level of utility U bar 1. So the agent gets the same amount of utility from every possible combination of bagels and coffee that lie on this line. Okay. Now, let me draw, I'm going to draw a couple more examples here of indifference curves, and then we're going to discuss. We're going to discuss how this works. So here's another indifference curve. We'll call this I2. And then, lastly, another indifference curve. We'll call this I3. Okay. Now, just to make sure I don't confuse us with indifference curves versus income, let's do indifference curve 1. Yeah, that sounds good. Indifference curve 2. Indifference curve 3. Okay, so now let's take a look at this and let's discuss. Now remember, with indifference curves, agents always want a bundle that lies on an indifference curve that's farther away from the origin. That means it's farther, let's just draw this out. They always prefer bundles that are farther away from the origin. And they always prefer bundles that are farther away from the origin because more is better. Remember that axiom, more is better. So the farther away the indifference curve is from the origin, the more utility that they get. Another way of putting it would be this. So if U1 bar is the amount of utility that the agent would receive from any bundle on the IC1 indifference curve, so let's put that, then the agent would receive more utility if they got a bundle on the second indifference curve, that is IC2. They would prefer any bundle combination on IC2, this indifference curve, than they would any bundle on IC1, that is this indifference curve. The utility that they get from the second indifference curve is greater than the utility they get from the first. And this goes the same for the third indifference curve. The third indifference curve is farther away from the origin. That means they would get more utility from any bundle that lies on that third indifference curve. So now if I asked you, let's do this. Here's a bundle, bundle A, here's a bundle B, and here's a bundle C. Would the agent prefer bundle A, bundle B, or bundle C? Well, we know that they would prefer bundle A. They would prefer bundle B to bundle A because bundle B is on a higher indifference curve. We also know that they would prefer bundle C over bundle B because C lies on a higher indifference curve. So they would prefer C. And in fact, we could go on forever. We could keep drawing new indifference curves forever upwards away from the origin. They would always prefer bundles that lie farther away from the origin. And so, without a constraint, the agent would consume an infinite number of coffee and bagels because they will always choose bundles that lie on indifference curves that are further away from the origin. Now this is where the budget constraint comes in. They can't buy any possible bundle. They can only buy possible bundles that they can afford. So now, just using this illustration, we can see that they would definitely prefer C. That's their preference. They would like to buy C. But now let's consider the budget constraint. Now let's think about the budget constraint. They would like to buy C. C gives them the most utility of the bundles that we've drawn here. However, we know that they cannot purchase C, because remember, any bundle that lies above the indifference curve is not that lies above the budget line, the agent cannot afford. The agent does not have enough money to buy bundles that are above the budget line. So it means they cannot buy C. They can't consume bundle C because it is beyond the budget line. So C is out. Well, let's see. What about A? Can they afford A? Can they afford A? Yes, they can afford A. They could afford A. Look, A is a bundle that lies within the opportunity set. It lies below the budget line. That means if they bought bundle A, they would be able to afford it. And in fact, they would even have some leftover income, because at bundle A, they are below the budget line. That means the agent is not spending all of their income. However, does A give them the most amount of utility? Well, no. We already said that B gives greater utility than A. And so, although they can afford bundle A, because it's within the opportunity set, it's below the budget line, they can afford A, but they still will not take it. They won't take it because there is still a better deal. Bundle B. Bundle B is within the opportunity set. In fact, it is right on the budget line. It's in the opportunity set right on the budget line. And it intersects with the indifference curve that is as far away from the origin as possible without exceeding the budget. So basically, they would choose bundle B. Bundle B would be the optimal bundle. They would choose bundle B. Okay, this is actually a little bit confusing. Let's turn this into bundle D, just to not confuse ourselves with bagels and coffee. I'm just going to turn this into bundle D. Okay, they're going to choose bundle D. Bundle D is some combination of bagels and coffee. Okay, they're going to choose bundle D. They're going to choose bundle D because it gives them the most amount of utility within the possible bundles that they can afford. That means D is going to give them the most amount of utility subject to their budget constraint. So bundle D will be the optimal decision. It gives them the most amount of utility, given the constraint. At bundle D, so we'll just call this, let's just give this little primes. It's at bundle D, income will be equal to, that means they're going to spend all of their money on bagels and coffee. Okay, so bundle D gives them the most amount of utility that they're able to achieve given the constraint, given their budget constraint, and they end up spending all of their money. So they maximize their utility by choosing bundle D. So right here. Now we can notice a couple things about this. Let's notice a couple things about this point, this bundle D. Notice that at bundle D, the indifference curve and the budget line are tangent to each other. That means they just touch. That means at that point, the marginal rate of substitution, that is, the slope of the indifference curve, is equal to the marginal rate of transformation, that is, the slope of the budget line. Now remember the slopes of these two. The marginal rate of substitution is the marginal utility of coffee divided by the marginal utility of bagels. Okay, and then the marginal rate of transformation, MRT, is equal to the price of coffee divided by the price of bagels. Okay. With that said, now we have a graphical interpretation, a graphical understanding of what we do when we're doing utility maximization. That is, we are looking for this bundle. We're looking for bundle D. We're looking for the combination of bagels and coffee that give us the highest level of utility that is possible given the budget constraint that we have. So we're looking for that bundle D. How do we do that mathematically? Well, that's what we want to do next. Let's give an illustration. I want to give an illustration of what it looks like to maximize the utility mathematically. What we're going to do is we're going to utilize constrained optimization, what we reviewed in the math review. So let's go there now. Okay. Utility maximization. We're going to look at it first in general terms, and then I'll do an example. All right, so let's say we want to maximize utility. We want to know how many cups of coffee and how many bagels will the agent consume in order to maximize the utility that they derive from it, subject to a budget constraint. That is, subject to the constraint of their income. They cannot buy more coffee and bagels than they're able to afford. All right, so subject to a constraint. Well, how do we do this? Well, if you remember, let's just do this generally first, is we set up the Lagrangian, or the Lagrange function, which has our utility function plus the Lagrange multiplier times the budget constraint times the constraint. Okay. All right, so we set up the Lagrange multiplier, and then we go through our steps, right? So we're going to find the derivatives, right? First step, we're going to find the derivative of the Lagrangian with respect to C, the derivative with respect to B, and then the derivative with respect to lambda. We're going to take all of these derivatives, we're going to set them equal to 0. That's step 2. Let's just get rid of that. All right. And then what we will do is we will solve them. We solve for C star, B star, and lambda star. All right. So that's just kind of an overview. That's how we approach this problem. That's how we do it. Okay. So if that's the case, why don't we do a quick example of doing a utility maximization problem. This will effectively be a review of constrained optimization or constrained maximization, but in this case where we are giving economic intuition or economic meaning to all of the variables and parameters in the model. So let's do that. All right, so now we're going to do an example. Okay. So what we want to know, we want to know how much coffee and bagels will the agent consume. We want to know how much coffee and bagels will the agent consume. Well, how would we go about knowing that? Well, we assume, according to rational choice theory, let's just spell it out. We know that according to rational choice theory, what an agent does, how they make this decision, the way in which they choose the number of cups of coffee and bagels is that they choose they choose C and B in order to maximize their utility. So if I want to know how much coffee and bagels they're going to consume, well, that means I need to maximize their utility function. I need to find C and B that maximize their utility function subject to the constraint, subject to their budget constraint. Oops. Okay. All right. So let's do this. Let's do this example. Do a simple example here. So let's set up the problem like this. Maximize C and B. And let's say that the utility function is the natural log of C times B. All right. Subject to the constraint. Income equals the price of C times C plus the price of B times B. All right. So let's do this problem right here. Let's solve this problem. How do we start? We start by setting up the Lagrangian. Okay, now you're going to notice, you should notice here that this equals the natural log of C plus the natural log of B. Okay? All right, natural log of C plus natural log of B plus Lagrange multiplier, income. So now our constraint is our budget constraint. Everything here has economic meaning now. Okay, and so now let's solve this. Step one, we've got to find the derivatives with respect to C, so that'll be 1 over C. All right, derivative of this minus lambda PC. Derivative of L with respect to B, 1 over B minus lambda PB. All right, derivative with respect to lambda. That's just going to give us our budget constraint again. All right. Now, second step, we create our first order conditions. That means we set all of our derivatives equal to 0. That's because that maximum point is going to be where the derivatives equal 0. So let's do that. And then we go to solving this set of equations we solve this set of equations for C star, B star, and lambda. Okay, so let's do that. So what we're going to do is I'm going to solve this equation here for C, this one for B. I'll plug them in here, solve for lambda, then take lambda, plug them back in. All right, so let's do that. All right, I'm just going to take the lambda PC to the other side. Okay, then I'm going to multiply both sides by C. So I'll get lambda PC C equals 1. Okay, and then I'm going to divide both sides by lambda PC. So then I'll get C equals 1 divided by lambda PC. All right, follow the same procedure here. Lambda PB. Now skip a step here and go straight to B equals 1 over lambda PB. Okay, well then now what I will do is I'm going to take these and I'm going to plug them in. And then I'm going to use this to solve for lambda. So let's do that. PC 1 over lambda PC. All right, minus PB 1 over lambda PB equals 0. All right, well, the PC's cancel out, PB's cancel out. I minus 1 over lambda minus 1 over lambda equals 0. Okay, simplify this. I minus 2 over lambda equals 0. Let's solve this. Let's solve this for lambda. Take I to the other side and then cancel out the negatives. So 2 over lambda equals I. All right, multiply both sides by lambda. 2 equals I lambda. All right, divide both sides by I, and we get lambda equals 2 over I. Now, how do we know when we're done solving? Sometimes that seems like it might be unclear. We know that we're done solving when we have the variable in terms of parameters. All right, there's no variable in here. We have the variable alone, and it is a function of only parameters. So now we can look at this and we say, that's done. We can put a star on it. Lambda star. So now let's take lambda star and plug them in here, and that will allow us to find C star and B star. All right, let's use this one. All right, so we'll just do this. C equals 1 over, now let's plug lambda in, PC, plug in lambda in, 2 over I. All right, what is that? Simplify 2, that's 1 over 2 PC divided by I. Well, that will equal I divided by 2 PC. Okay, now I have C in terms of only parameters. That means I'm done. Let's do the same thing for B. 1 over PB times 2 over I. I can skip some steps this time. I go straight to I over 2PB. All right, so then if I want to summarize, let's summarize all the results. C star equals I over 2PC. B star equals I over 2PB. And lambda star equals 2 over I. Okay, so now we've just done utility maximization. We have found the value of C, B, and lambda that maximize utility. That if I wanted to say, how many cups of coffee will the agent buy? Well, this many cups of coffee. This is the number of cups of coffee that they would buy, because that's the amount of coffee that maximizes their utility. If I asked, well, how many bagels will they buy? Well, this is the number of bagels that they will buy, because that's the amount that maximizes their utility. Okay, so that is our first example of a utility maximization problem. And that will be it for this lecture. Stay tuned for next time, where we go a little bit deeper into the utility maximization problem, and we discuss the indirect utility function and a number of other interesting facets of utility maximization. Okay, thank you. Have a great day.